Good evening, everybody. Hey. That's better. Yes, Gaia, the space mission Gaia, 5-year mission to map 1 billion stars. It was so successful at doing that, they decided to make it a 10-year mission to map 2 billion stars, which it did very successfully. So I'm talking about why we bother mapping the stars in the Milky Way, how that can be done accurately, what type of data you can acquire, and what do we do with the shed loads of data that have been coming out of Gaia for the last decade or so. So to start with, why map the stars? Well, there's the very trivial reason that we want to make star atlases, so we want to know where the stars are, so that we can find things at a later date by going back to a star atlas, and we can tell if something has moved or changed brightness, and we can tell if new objects have appeared. But you could argue that's a rather trivial reason for wanting to map the stars. We really want to map the stars because if we can do so accurately, then we can get a pretty good idea of how the Milky Way is put together, both where things are and the dynamics of how stars are moving, as well as the history, the evolution of how the Milky Way ended up looking the way it does. So how do we go about mapping all the stars? Do we simply take lots of pictures of the sky and mosaic them all together? That works fine for the Earth, but it doesn't work for the sky because of two specific problems. One, not anything in the Milky Way galaxy is static. Everything is on the move. We may not think of the stars moving much in the sense that apart from the fact that the Earth rotates and the stars appear to move across the sky, we don't see the stars change their position much from day to day, year to year, but they are all moving through the Milky Way galaxy. And that is what we're trying to measure. So simply taking lots of pictures and trying to stitch them together won't work because everything is on the move. The second reason we can't simply take pictures is because we have to accept the fact that we are dealing with a three-dimensional problem. The stars are all at different distances. So although we might see a constellation as a particular pattern in our sky, we have to remember that all the stars are at various distances. And if we want to understand the structure of how stars are moving through the Milky Way, we need the full three-dimensional information. We need to know where they are on the sky, and we need to know their distances. Could I just interrupt for a second and ask, is it possible to have a glass of water? Thank you. So we want to know distances as well as positions in the sense of two-dimensional positions. But distances are actually critical not only so that we can understand where things are in the Milky Way, it's actually critical simply to understand stars themselves. Because if you think of the familiar way of classifying stars by plotting them as a function of their luminosity on the vertical axis and their color on the horizontal axis, well, if we don't know the distance to a star, we don't know its luminosity. How can we tell if it's a bright star a long way away or a dim star relatively close to us? If we do not know distance, we do not know luminosity. So if you imagine, for instance, let's say we were looking at a very interesting blue star, but just because it's blue, well, does that mean it's a supergiant or main sequence or a white dwarf? If we're looking at a red star, how can we tell if it's a red supergiant or a red giant or a red dwarf? We can get hints from the spectra, but without knowing the distance accurately, we cannot accurately determine its luminosity. We can only get its apparent brightness, not its absolute brightness.
The glass is slightly wet. So.
Thank you. So we want to know distance more than simply for wanting to understand the dynamics of the Milky Way, simply to understand what the stars are and how they evolve. Are our theories about how stars evolve, are they correct? If we can determine exactly where they are in the Hertzsprung-Russell diagram, we can figure out how stars evolve. Not only that, but as a bit of an aside, bear in mind that if we don't actually know what type of star we're dealing with, is it a red giant or a red dwarf, well, actually, we can learn almost nothing about any exoplanets that happen to be going around that star. Remember, when we're dealing with exoplanets, we look at the wobble of a star produced by a planet, which depends on the planet's mass, strictly the planet's mass relative to the mass of the star. And similarly, when a planet transits a star, it blocks light from that star. And how much light does it block? Well, it depends on the size of the planet relative to the size of the star that it's transiting. So if we don't know the size of the star or the mass of the star, then effectively we don't know anything about the exoplanets either. So we want to know distances for a lot of astronomical or astrophysical reasons. And distance ultimately comes from parallax. Perhaps you're already familiar with this idea. There's the old classic idea of hold up your finger, blink your eyes, and something that's close to you, like your finger, appears to jump backwards and forwards relative to more distant objects. And parallax is often described as it is simply the movement of a nearby star relative to a distant, brackets, fixed star. But one thing we have to bear in mind is there's no such thing as fixed stars. We are trying to work out where all the stars are in terms of where they are and how they are moving. So unfortunately, although this diagram implies that if we want to measure the so-called parallax angle, as shown on the right there, the apparent change in the position of a star as Earth goes around the sun, ideally from two ends of its orbit, but as it goes around the sun, basically all stars will trace out an ellipse or something close to a circle. The parallax angle is very small, but how do we measure the parallax angle when the fixed stars themselves are moving? So that is a problem. If everything in your field of vision is moving, parallax is not as simple as that diagram would have you believe. Remember also, the angles are quite small. Hypothetically, if a star was at about 3 light years, it would have a parallax angle of 1 second, 1 arc second. So remember, this diagram is enormously exaggerated in the sense of if the distances to the stars were correct, then the Earth-Sun distance would be tiny. 3 light years would give a parallax angle of 1 arc second, and that's how we define 1 parallax second as the distance where your parallax would be 1 second. That 1 parsec is 3.2 thereabouts light years. And of course, no star is actually that close. Closest star is over 4 light years. So no star has got a parallax angle greater than an arc second. And if you go to hundreds or thousands of light years, then the parallax angles we're talking about are tiny, milli-arc seconds rather than arc seconds. So we might be used to the idea that arc second means that's really good seeing. If we look through an amateur telescope and we see detail at the level of arc second, we're really doing well. But we really need measurements if we want to measure distances to stars to much better accuracy than that. So here's the crux of the problem. If we want distances, then the only way of getting distances to the stars, the only feasible way of getting distances to the stars is this idea of parallax as the Earth moves around the sun and the different perspective of what do you see when you look from different points in the Earth's orbit. To calculate distances, absolutely we need parallax, but parallax needs to know where the star actually is, not where the star appears to be relative to a few stars behind it, which are also moving. So you need an absolute frame of reference, not simply let's map out where the stars are relative to each other. That's not good enough. Third problem, the stars themselves are moving. Everything in the Milky Way galaxy is in motion. Some things are moving fast, some things are moving slow, but nothing is actually static. So we have 3 problems. We need parallax. Parallax needs actual positions, and the stars themselves are moving. So how can we possibly work out how a star appears to be moving as we go around the sun, and also take into account the fact that the star itself is moving? That is why mapping the Milky Way is not a trivial task. That is why it's something that we could not have done until the last few decades when the technology allows us to do that. We would like to have done it 100 years ago, but we couldn't effectively. So how do you go about mapping accurately? We have to untangle the fact that stars apparently move due to parallax, but also actually move because they are moving through the Milky Way. One is an apparent motion because of the motion of the Earth. The other is an actual motion of the star. We've got to disentangle those 2 things because both of them give us information. One tells us about what the Milky Way is doing. The other gives us distance, which is useful for the 3-dimensional nature of how we map the Milky Way and useful for astrophysics as well. So we need very high precision measurements. I've said high precision, I should have put a very in there. We need very high precision measurements if we're going to do this. And we need a fixed coordinate system because nothing is static. Parallax angles are very small, as we will see very shortly. And if Earth is in motion and stars are in motion, then we need a fixed coordinate system to allow us to disentangle that mess. Just as an aside, it was thought back in the 1980s, why don't we make this job easier? Instead of relying on the Earth going around the sun for our baseline to say things look different as we go backwards and forwards and I can see positions change, why don't we have a baseline which is much bigger? Let's send a spacecraft out 1,000 AU, 1,000 astronomical units. So they said, we can do that. We can put an ion drive and send it out into the solar system. It'll only take 50 years. If they had launched it in the 1980s, it would still be on its way. They decided not to do that. Just as a reminder, Voyagers have only got 150 astronomical units even now, having been launched in the 1970s. So they thought about it, but decided not to do that, which was probably the right decision. Okay, so what coordinate system are we going to use? We can't simply measure star positions relative to each other. We need an absolute coordinate system. You're probably familiar with the idea of right essential and declination. They are effectively extensions of the Earth-based system. The celestial equator is simply an extension of the Earth's equator. The north celestial pole and south celestial pole are just extensions of the Earth's north and south pole. So it's a coordinate system intimately linked to the Earth. We've been using right ascension and declination, or RA and DEC here. We've been using it since the days of the first Astronomer Royal. What's the problem with using right ascension and declination? Every star atlas has got that, so what? Look, we look at a star atlas and there's the grid system, there's the right ascension and declination. So in principle, we can read off the coordinates of any star. Well, yes, but remember, I'm not sure what your first star atlas was. There's Star Atlas, Norton Star Atlas 1950 and 2000. Those are not the publication dates of the Star Atlas. They're the epoch dates. They're the dates at which the coordinates of the stars are either given or calculated. So why should they be different in 1950 and 2000? Well, they're different because the Earth moves. It doesn't simply spin. Its axis precesses over a 26,000-year period, which means even if you know very accurately the right ascension and declination of a star now, it'll be different tomorrow, and different the day after, and different the day after, because the Earth's axis, and hence the right ascension and declination coordinates that we use, will continually drift over a 26,000-year cycle. So fixing coordinates to the Earth, not a good idea. Okay, you might say, right, let's use the sun then. Well, actually, that also would lead to small errors because the sun also moves in the solar system. If we plot the motion of the sun, we find the sun here in a rather exaggerated sense. The animation is just slowing down so we can see what it's doing as we approach the late 2020s. The position of the sun changes simply because the planets are counterbalancing, if you like, the sun. Back in the early 20s, the sun was actually quite a long way from the center of the solar system, simply because all the big stuff, Jupiter and Saturn, were over on the other side of the solar system, and so they were counterbalancing. When Saturn and Jupiter are spread through the solar system, well, the sun is then a little closer to the center of the solar system. So the center of mass of the solar system is called the barycenter. There it is right in the middle. And although we're always taught, yes, the planets go round the sun, no, they don't. The planets and the sun all go round a common center of gravity or center of mass or barycenter, as it's often called in astrophysics. And hence, given that we know the sun moves, the ideal system to use is not the sun, it's the center of the solar system, the barycenter, and we can calculate where that is quite accurately because we know what the planets are doing. We've been monitoring what the planets are doing, and we know where they're moving, how they're moving, so we know where the center of the solar system is. Now we've got a fixed reference point. Regardless of where the Earth happens to be in its orbit, we're going to calculate the positions of these stars as they would be seen as if we were standing in the barycenter, which effectively doesn't move as the solar system does its stuff and the planets go around the sun. Correction, the planets go around the center of mass, as does the sun. If we were to imagine what does the sky actually look like if we exaggerate parallax every object in the sky, as the Earth goes around the sun, will appear to move in a circle. Every star will trace out a circle, or possibly an ellipse, depending on the angle we're looking at it. And if the star is quite close, it'll appear to be a big circle. If the star is quite distant, it'll appear to be a small circle. So if we measure all the star positions and see how big that circle is, we can work out the distance, because that's effectively the parallax angle. But not only have we got parallax, we've got proper motion as well. The stars are actually moving. So in fact, the sky actually looks like this. Every star is in motion, and every star is undergoing a small circle because of parallax. And therefore, every star in the sky is corkscrewing through the sky. You tend not to think about that because it's a very small corkscrew, and you need very high precision to be able to measure the corkscrew. And if you can measure that corkscrew and get enough data points on that corkscrew, then effectively you can disentangle the circular motion produced by the Earth, which gives you the parallax, which gives you the distance, and separate that from the linear motion. Not every star is necessarily traveling in a dead straight line, but we're talking about measuring it over a few years. And remember, it takes hundreds of millions of years for stars to go around the Milky Way. So over a few years, every star is essentially traveling in a straight line. And therefore, we want to measure the corkscrew, and then we can disentangle the straight line from the circle, which gives us everything we need to know about that star. The first satellite that tried to do that was Hipparchus, back in the late 1980s, early 1990s. You can see the acronym at the top there. I think they said, let's have a homage to Hipparchus the Greek, and what can we do with an acronym that gives us something close to his name? So they came up with High Precision Parallax Collecting Satellite. It was the first telescope dedicated to, can we measure the stars accurately using a spacecraft above the atmosphere to get rid of all of the problems of trying to measure things accurately from ground level, where we have the problems of a turbulent Earth atmosphere. Hipparchus catalogued something like 100,000 stars, and it did it with milli-arcsecond accuracy. So remember, arcsecond is what we normally think of as a fairly small angle, 1/60th of an arc minute, which is 1/60th of a degree, etc. But here the precision was milli-arcsecond, and it measured the positions of stars down to about magnitude 12. And the Hipparchus catalogue was actually the first catalogue used as the reference catalogue for the Hubble Space Telescope, so that the Hubble knew exactly where it should be pointing. So lots of stars, hundreds of thousands of stars across the sky, used to make sure Hubble and then other telescopes were doing their job properly. That was Hipparchus a few decades ago. And now we get to the main event, Gaia. Now, the acronym for Gaia, I won't even bother reading it out because it doesn't matter anymore. They invented the acronym when they thought they were going to use interferometry to do the measurements. They then changed their mind, but they thought it's such a wonderful name, let's keep the name anyway. Means you don't have to change the domain from gaia.com to something else. So the acronym is no longer relevant, but the intention was that Gaia would be a spacecraft that would improve on Hipparchus, because technology has moved on since the 1980s and 1990s, and now we are capable of building a machine that gives us the positions of stars to an accuracy, a nominal accuracy of 10 micro-arc-seconds, where a micro-arc-second is 1/1000th of a milli-arc-second. And the high precision, remember the parallax triangle, if you've got a parallax angle that's very small, that corresponds to a great distance. If you can measure that parallax angle very accurately, you can measure distances with a greater reach. In other words, you can determine the distance to more distant stars if you can measure that parallax angle accurately. If you can only measure parallax to 1/10 of an arc second, you can't really measure stars other than our immediate neighbors. With this sort of precision, you can start measuring stars way out into the galaxy. And it had a limit of order 20, magnitude 20, compared to Hipparchus's 12. So it can determine the distances to much fainter stars. Now, 10 micro-arc seconds is phenomenal, but it's difficult to gauge just exactly what that means. 10 microarc seconds, 0.01 milliarc seconds. Let me give you an analogy that tells you just how ridiculous that precision is. It's equivalent, when we're thinking about an angle, it's equivalent to the thickness of a human hair as seen from a distance of 1,000 kilometers. Imagine you were standing in Land's End looking at somebody at John O'Groats. It's the equivalent of saying you're going to determine the position of that person to an accuracy of the width of a human hair. Phenomenal and very underrated. Some people have dismissed Gaia as all it's doing is measuring star positions, but it's doing it with that crazy precision. So why build a telescope to do that? Can't we get that sort of precision from anything else? Can't we map the sky with one of the telescopes we've already got? We've got some wonderful telescopes. We've got the Hubble Space Telescope. We've got the Chamonix Telescope, otherwise originally known as the LSST, the Large Synoptic Survey Telescope, the telescope that's sitting in the Vera Rubin Observatory. Well, Hubble certainly is capable of very high resolution measurements of order milliarc second, not as good as Gaia. And certainly the Chamonix telescope can indeed map billions of stars, because that's its job, to map billions of stars, tens of billions of stars, in fact. But Chamonix doesn't have the resolution. Chamonix will only have resolution of a fraction of an arc second. And Hubble, despite having phenomenally good resolution, has only actually measured the parallax of something like 1,000 stars or so. So if you asked either of those telescopes to actually map 1 billion stars, well, Chamonix could do it in 10 years, but it wouldn't have anything like the accuracy we want. And if you want the Hubble Space Telescope to do it, it could do it as well, but it would take about 5,000 years or so. And its gyros are not going to last that long. It's already been up there for 35 odd years. It's not going to last. So no other telescope could possibly do what Gaia does. How does Gaia achieve this phenomenal accuracy of mapping stars? Gaia is an ESA project. Hurrah, it's European. No NASA input, if I understand that correctly. It was put together by a company called Astrium, which took input from lots of companies across Europe. The optics were built in Germany and France and Belgium. The detector was built in the UK. Hurrah, some of the electronic systems were built in the UK. Everything was then sent to Astrium in Toulouse for final integration. Astrium, perhaps a name you've not heard of before, it's now part of Airbus. It was constructed in the late noughties, early teenies. It was launched in December 2013 and was then placed a few months later in orbit around L2. It nudged the James Webb, well, James Webb sort of nudged Gaia, I guess, in the sense of they're both trying to orbit L2. Let's just remind ourselves, if we ignore the other Lagrange points, L2 is there 1 million miles above midnight, and Gaia was sent there for the same reason that James Webb was sent there, because it's a nice place to get away from the moon and the Earth and the sun. With a single sun shield, you can block the light from moon and sun and Earth. Effectively, there's nowhere else you can do that. So L2 is the preferred place to send spacecraft these days. The sun shield itself, you can see here being tested. It also gives you an idea of scale. You can see the technicians running around like bees there. You can see the sun shield is something like 10 meters or so across. They tested it like the James Webb, not as sophisticated as Webb's sun shield. So they simply tested that it did indeed operate as it should, such that after it was packed up for the rocket, it would extend the sun shield correctly to protect the mirrors from the light of the sun. We come back to the question. We know that large mirrors produce high resolution. That's why James Webb has got a large mirror compared to the Hubble. But how do you achieve micro arc second resolution? Do you need a mirror a kilometer or so in diameter? Well, clearly not. We've just seen that Gaia is only a few meters or so in size. So we can't possibly use a large mirror, so what tricks do we come up with to give us the resolution without having a large mirror? Just as a reminder, there's the largest telescope in the world at the moment, Gran Telescopio Canarias on the Canary Islands, with something like a 10-meter diameter. Okay, it's segmented, so it hasn't technically got a diameter, but you know what I mean. All the space telescopes are down there in the bottom left-hand corner. Let me make them a little bit bigger so you can see them more clearly. There's Gaia, along with Kepler, James Webb, and Hubble. And you can see Gaia has got amongst the smallest mirrors of all of those telescopes. Basically about the same size as Kepler, but certainly no bigger than Hubble and a lot smaller than James Webb. And perhaps also rather oddly, rectangular mirrors, and we'll see why very shortly. So Gaia achieves its high precision not by having humongously large mirrors, but by an ingenious combination of instrumental hardware and the way that that hardware is used, the operating mode. So firstly, what hardware does it have? Well, it has a very large detector built by E2V in the UK. It's a detector comprising 100 or so CCD chips, each of which is 9 megapixels. So it's got an awful lot of pixels to play with. And I said Gaia was a telescope, but technically Gaia is 2 telescopes. It has 2 mirrors and has 2 telescopes, and those 2 telescopes point to different parts of the sky, and we'll see why that's important in just a second. Now, how does it operate? This is the way that makes Gaia different from anything else that's out there. Both telescopes create images which fall onto the same detector. And at first sight, that sounds ridiculous. Why would you have 2 telescopes and take the images from those 2 telescopes and stick them on top of each other? Doesn't that confuse matters? It is integral to the way Gaia operates. And the other point is that these 2 telescopes are pointing at different parts of the sky, and Gaia rotates. Gaia spins, and those telescopes sweep out the sky. Gaia does not take images. Despite what you might have seen, Gaia does not take images. It measures where the stars are. And that makes Gaia very different to the sort of telescopes we're used to, where you have Hubble or James Webb, which points at a patch of sky and takes a picture of what is there, and then you see a nice image showing you stuff, whether it be stars or nebulae or galaxies. The way data comes off the chip is different between the way Gaia operates and the way every other space telescope operates. So it's worth taking a close look at exactly what's going on there. A CCD is shorthand for a charge-coupled device. What that means is when light hits one of these chips, the light is converted to an electric charge. And the amount of electric charge that's generated should be proportional to the amount of light that hit it. So if we can measure how much charge there is in each pixel on that detector, we've got a measure of how much light hit that pixel. And the question is, how do you go from a detector full of electric charge to what you want, which is a whole load of numbers which represent how much light hit each pixel in the detector? How do you go from a chip to all of the data? And that is what's different about Gaia. So let's remind ourselves how it works in the conventional sense. By conventional, I mean the way you expect cameras to work. Imagine a field of view containing a star field. How is the image made? Well, remember, the image that we want effectively is just the numbers telling us about how much light. Most CCDs that you've heard of work in so-called stare mode. In other words, the Hubble Space Telescope, or whatever it happens to be, is told to point at a particular object and stare at it. In other words, you hold the telescope absolutely rock steady, which is what the gyros on the Hubble are responsible for making sure it always points in the same direction. If you've got an amateur telescope, then it's probably on an equatorial mount to make sure that it always points to the target you're interested in, even though the Earth is rotating. So what that means is you point at an object and you expose the CCD to light, and slowly the image builds up over seconds or minutes or hours, and eventually you've got the data. Once you've got the data, you read it out. The pixels are shuffled down into a register, and then that register is read out 1 pixel at a time. How much charge? How much charge? How much charge? That is electronically measured, and the results are stored. Then the next row of pixels is shuffled down, and then the pixels in the register move through and are read out. It takes about a millisecond to shuffle all of the data down. It takes about a microsecond to move each pixel along and read it to see what the light level was. And so it can take seconds to read millions of pixels. It'll depend on exactly how the system is configured. After a second or 2 or 3, all of the charge that was in the CCD has now been read out through this sort of bucket brigade idea of the charge being transferred. That's why it's called a charge-coupled device. The charge is coupled from one line to the next, 1 pixel to the next. After that's finished, you're now left with a whole load of data, and assuming you know how it was read out, you know exactly what any individual bit of data corresponds to in terms of where on the chip it came from. That's how normal CCDs work. You stare at a patch of sky, you record, and when you're done, you read it all out. That's not how Gaia does it. Remember, Gaia is on the move. It's continuously spinning. The telescopes are sweeping through the sky. If you tried to use stare mode, the stars would simply blur as they moved across the CCD. So Gaia is spinning, which means the stars are continuously moving across the CCD. The clever bit about how Gaia works is that the CCD is continuously read out. It is continuously shifting exactly in synchronization with how the stars are drifting across the CCD. So the star always stays in the same pixel till it reaches the end. Once it reaches the end, the pixels are read out, and when you find a star, you make a note of the time that happened. So Gaia is not taking pictures, it's actually recording the times at which stars arrived at particular points in the detector. And it effectively is doing that continuously. I showed what happened for 1 star. Of course, there are lots of stars. Every millisecond, lots of stars will have their timings measured. Lots of stars, every millisecond, for 10 years. That's an awful lot of data. And the timing is done by an onboard atomic clock. You need timing of order microsecond accuracy to know exactly when each star arrived at particular points in the detector. Let me deal with this oddity of why has it got 2 telescopes but 1 detector? What is the point of that? Well, you probably have heard of another device which is 2 telescopes and 1 detector. It's called a sextant. Now, sextants are great for navigation. I'm guessing you've probably got one in your boot in case your GPS ever fails, just to be on the safe side. How does a sextant actually work? Well, it's a little telescope and a couple of mirrors. And the idea is you point it at the horizon, and the light from the horizon goes to the telescope, and you look at it with your eye. Now you're interested in where a star is in the sky. Well, it might be the sun or the moon, but let's assume it's a star. A star might be quite a few degrees above the horizon. You can't look at the star and look at the horizon. Look at the star and look at the horizon. You can't do both. But if you've got mirrors, you can reflect the light from the star such that the star appears to be on the horizon using semi-silvered mirrors. 2 different points of the sky, but arriving at the same detector, your eyeball. Now, in the case of navigation, you're interested in that angle because that angle gives you your latitude and it allows you to navigate. But the point here is light from 2 objects has been bounced off mirrors such that they end up at the same place. This means you can determine the angle between the star and the horizon very accurately because you can read it off that vernier scale at the bottom. It doesn't matter if the boat is going backwards and forwards or to and forth. It doesn't matter because the star and the horizon are being brought together So it doesn't matter if the if the boat is moving around and you're having difficulty trying to keep your sextant pointed in the right direction. It doesn't matter. The angle between the star and the horizon, which is all you care about, is read off the angle of the sextant. Same for Gaia. It's got two telescopes that are pointing in different directions, and by bringing the light from both telescopes to the same detector, we can measure stars in different parts of the sky and get their relative position extremely accurately. If we try to do that piecemeal, where is this star relative to that one? Where is that star relative to this one? Where is that star relative to that one? All the errors would add up. By looking at different parts of the sky simultaneously, by having the light arrive at the detector at the same time, gives us the accuracy we need. So that's what a naked Gaia looks like. This is Gaia without its coverings. Two primary mirrors, each of which are rectangular. They're rectangular because we want very high precision in one direction, and we're not that fussed about the other. We need very high precision in the direction we're spinning because we want that timing to be as accurate as possible. So there's an idea of scale. There's the Astrium technicians starting to put it together. The big donut, if you like, is an optical bench. It's designed to keep those mirrors and everything else in Gaia absolutely fixed in position. We need to keep the temperature constant. That's one reason for having a sun shield. You can't allow the temperature inside Gaia to change by 1,000th of a degree. That would be way too much. You would have to keep the temperature fixed to much less than 1,000th of a degree to make sure there's no thermal expansion or contraction of anything in that optical bench. Let's look at the array of CCDs in the detector. There's a whole batch of so-called astrometric CCDs. These are responsible for the timings. When a star reaches the edge of one of these CCDs, the timing is determined. We'll see that in just a moment. As well as astrometrics, let me just say the CCDs themselves are not that big, 5 by 6 centimeters, and each of them is 9 megapixels. The pixels themselves are rectangular. Remember, the mirrors are very high resolution in one direction, not such high resolution in the other, so the pixels are manufactured to suit. There are a couple of so-called sky mappers. What are the sky mappers? They are chips whose job is to tell which telescope produced this star. Because both sets of stars are effectively hitting the same detector, before they end up on the astrometrics part of the detector, a system has to know, did this star come from telescope 1 or did it come from telescope 2? Then it can monitor how those stars move across the rest of the detector. So sky mappers are responsible for effectively IDing which telescope. After they've been through astrometrics, the light from the stars goes through a prism so that we can work out how blue is the star and how red is the star. Remember the Hertzsprung-Russell diagram. If we know the star's color, we know what type of star we're dealing with. For some of the stars, the light will also go through a spectrograph so that we get the full spectrum of the star as well. There are a few other chips in there responsible for, well, making sure everything stays in focus, making sure that the angles between the two telescopes is absolutely what we think it is, and there's no variation, because that's critical to Gaia's operation. And just to give you an idea, if we think of the stars drifting across the CCD, well, it takes about 4 seconds for a star to drift across a single CCD. Remember, a 9 megapixel CCD. So it takes about a minute for a star to drift across the entire detector. So let's have a look at the operation. Here's a nice ESA video. We can imagine the two fields of view being color-coded in cyan and magenta, just to give us an idea of which is which. Let's look at the light coming from telescope number 1. As the telescope light hits the main mirror, it bounces off a lot of mirrors before it finally hits the detector. The focal length is about 35 meters, so it really has been folded. And then the light from telescope 1 hits the detector, and Sky Mapper 1 tells us we've got stars from that telescope. Simultaneously, telescope 2 is looking at a different patch of sky. That gives us the magenta stars, and they hit the same detector, but now Sky Mapper 2 tells us these are the stars that came from telescope number 2, and they drift across. If we watch what happens as a star moves across, it is tracked. It gets brighter and brighter and brighter as the image builds up. When it reaches the end, you record the time. Then it goes through the next CCD. It gets brighter and brighter and brighter. When it reaches the end, you time it with the atomic clock. And you do that again and again and again and again. Gaia gets some of its precision by repeated measurements. Once the star has gone through the astrometrics, we see how blue is it, how red is it, and depending on which stars, because we can't do them all, some of the stars will have their spectra recorded as well. So if we see what that looks like in practice, stars are hitting all over the place. Stars are being recorded in the sky mappers, being logged as we've got a new star, let's track that, we've got a new star, let's track that. This particular little cartoon shows about 24 stars moving across the detector. In practice, there's more likely to be 500,000 stars moving across the detector at any given time. And in any given second, thousands of stars will be reaching the edges of these CCDs where their brightness will be recorded and the microsecond timing of when they arrived will be recorded as well. So this is the idea of, for any given star, we are taking multiple measurements of its brightness and the timing of when it arrived, as well as its color, as well as possibly its spectrum. That's why, even though we might only be measuring 1 billion stars, we're actually making trillions of measurements along the way. Gaia, I said, is spinning. It's actually spinning not that fast, not as fast as the animations would have you believe. It's actually spinning once in 6 hours. That gives you a star moving across the detector in about 1 minute. So it's spinning, and so it's mapping out a ribbon of the sky by spinning, and that ribbon of sky, because Gaia is precessing, starts to sweep out until it eventually covers the whole sky over a period of months or possibly years. So different parts of the sky are being covered multiple times, and the color here in the bottom right gives us an idea of how often that particular patch of sky is being imaged. And not every bit of sky is imaged the same amount, but all of the sky is imaged quite a few times. I shouldn't really say imaged, it's being measured quite a few times to give us an indication of where those stars are across the entire sky over a period of years. So what data was acquired? The original mission from about 2014-ish to nearly 2020 was extended. The original 5-year mission was extended to a 10-year mission, so it went roughly from 2014 through to more than 2024. Lots of data, but remember the data is shed loads of timings. Then some poor soul has to try and work out, so where are the stars then? If you've got 1 million timings and you know how Gaia is moving, you can work out where the stars must have been in order to give you this set of timings. But it is a horrendous computational problem. It's still the best way of doing it to give you the accuracy you need, but it takes time to reduce all of the measurements taken to a catalogue of this is where we think the stars are. So although it started back in 2014, it was a while before they got the first data out. Data releases, there are planned 7 data releases, numbered. You think they might call them 1, 2, 3, 4, 5, 6, 7. No. 1, 2, E, 3, F, 4, 5 are the data releases. Data release 1, because the scientists were getting very antsy and wanted some data, data release 1 only contained the first year's worth of data. So it hadn't necessarily mapped each star many times over. It certainly got a few dozen measurements for each star, but it hadn't been back to that star month after month after month after month. It only revisited each star a few times. So it had the coordinates of millions of stars. And by coordinates, I mean the position on the sky and the distance, by determining what the parallax was and hence getting an estimate of the distance. But the more data you take, the more accurately you can figure out where the stars are. Gaia is all about repeated measurements, and the more data you take, the smaller the errors that you then determine. So data release 2 took the first 2 years worth of data, and instead of getting nice data on 1 million stars, it got some nice data on 1 billion stars. So it had already met its design parameters of mapping 1 billion stars. It hadn't quite got them as accurate as the astrophysicists wanted, but after crunching 2 years of data, which came out in 2018, they had some data on billions of stars, which gave them a foothold. Scientists were definitely getting antsy, waiting for yet more precision. They wanted data release 3, but it was decided, well, data release 3 isn't going to occur until about 2022, and some people just didn't want to wait that long, so they had an early data release using 3 years' worth of data to improve the precision. Improved precision of where the star is in the sky, and hence greater precision to the parallax, size of circle, as well as the precision of where is the star and how is the star moving. We can now start to get information about how fast the star is moving, because we've now got star positions over, in this case, 3 years of those measurements. Eventually, data release 3 came out, which was the precision that we had before, but in addition, they then said, well, actually, we found lots of interesting things as well as where the stars are. We've actually determined that millions of these stars are variable stars, many of which we didn't know were variable, because we can now measure the brightness of the star over a period of years. Still only 3 years worth of data, but over 3 years, we've measured the brightness of these stars accurately enough that we can determine that they are variable stars. And we're looking at effectively small blobs, which might be stars, but some of them might be very distant galaxies. So in fact, they picked up millions of galaxies as well. Some of these galaxies were very useful because it was known that these galaxies are very remote. Quasars, very bright galaxies, but billions of light years away. And remember, parallax angles and the amount of motion you can expect depends on things being close. A quasar is so distant, being 1 billion light years away or something like that, then there's no way that you're going to measure the parallax, and there's no way that that quasar is going to move to a different part of the sky over a period of a few years, which means effectively you have a fixed point in the sky. Hurrah, we've now got our fixed stars. They're not stars, but they are fixed points in our data set, so that we can say, if these are where the stars are, and we know that these quasars are in fixed points in the sky, and we measure everything relative to the center of the solar system, we now have a fixed coordinate system, which improves the accuracy no end. Along the way, we've also got 100 million spectra. In other words, we've got 100 million stars whose spectra are now determined, far more than we had by measuring star spectra from ground-based telescopes. And by accident, we've also found a few solar system objects, because again, small asteroids are going to look like stars, and we can determine that they are solar system objects just by the way they are moving compared to the way the stars are moving. So they found something like 100,000 solar system objects. Some of them they already knew about, some of them were new. The next data release was a focused product release, the F release. What they did is to say, well, data release 4 isn't ready yet, but we've got 5 years of data that we're now plowing through. Data release 4 is going to come out this year, hopefully, but before data release 4 is ready, we're going to look at the first 5 years of data from Gaia, and we're going to do various things, but one of the important things we're going to do is look at Omega Centauri. Omega Centauri is a globular cluster. This is an image, I can't remember if it's a Hubble image or not, but some globular clusters are extremely crowded. Omega Centauri has probably got millions of stars in it, and it is so crowded it's difficult to make out individual stars. Even Hubble can't make out individual stars right in the core of something like Omega Centauri. So the Gaia people said, let's see what we can do to refine our techniques such that we can see what's going on, even though stars are really, really close together. What they want to do is to be able to look at stars very close to the center of the galaxy, which is a really tough ask. So they're using Omega Centauri as a touchstone. Let's test our ideas, let's test our algorithms on Omega Centauri to see if we can see detail in there. And if we can, that will allow us to refine our analysis and hopefully be able to look at stars close to the center of the galaxy. Data release 4, not yet out. It should be in 2026. I'm not sure what the schedule is, but perhaps a little bit towards the end of the year. And data release 5, not until, according to this diagram, 2030. It's going to take them that long to analyze all of the data. The final data release will be all 10 years of Gaia, and that will be, hopefully, everything at the full resolution of which Gaia is capable. Let's remind ourselves what it is we're dealing with. This is the best model that we have of the Milky Way, updated because Gaia has now given us some information about where stars are, not across the entire Milky Way, but over a reasonably large chunk of it. These are the distances relative to the center of the galaxy. The yellow dot there is where we are in the Orion arm. I think it used to be called the Orion Spur. Seems to have got a promotion. It's now an Orion arm rather than Orion Spur. We're about 8 kiloparsecs or 25,000 light years from the center there. If we think about what happened with Hipparchus, all of the stars that Hipparchus satellite found were inside the yellow dot there. So in other words, they were very much local. The 100,000 stars that Hipparchus saw were, remember, only the bright ones and only the relatively close ones. So we didn't really get a sampling of the galaxy. Hipparchus only gave us an idea of what stars look like in our immediate neighborhood. Data release 2 of Gaia out in 2018 extended the range over which we could measure parallax accurately and hence determine distances to stars, so that we ended up picking up all the stars inside that green circle there. Still relatively local to our own spiral arm. As soon as we go to data release 3, we now have 3 years worth of data. The accuracy improves considerably, and if accuracy improves, that means we can measure parallax to much greater distance. So the green circle got bigger. Data release 3 was phenomenal. Data release 3 basically covered not quite half the galaxy. I'm not saying that it covered every star in half the galaxy, but it did include some bright stars out to that sort of distance. It still struggles to figure out what's going on in the center of the galaxy, so that circle is only schematic. If you like, there ought to be a little notch taken out because we still can't really see what's going on in the center of the galaxy. But it gives you an idea of the range over which Gaia has now got information about stars in many of the spiral arms on this side of the Milky Way. So this looks like an image, but it's not. You might have seen this before when Gaia has mapped the Milky Way. This often appeared in their public relations output. It's not an image. It's actually a map in the sense that every pixel is not how bright is the star or how bright is that particular part of the sky. Each pixel is basically lit according to a brightness, which is how many stars did Gaia find there? And hence, it's finding, of course, a lot of stars in the center of the galaxy, not so many stars up there, quite a lot of stars in the large and small Magellanic Cloud, etc. So it's really just a star count. And yes, the dust will mean that you get less stars in those directions, and hence you get dark areas. So it does look very much like an optical picture, but it's not. So what can we learn from all the data that we've been getting out of Gaia? Remember the Hertzsprung-Russell diagram. Now we're not guessing what the Hertzsprung-Russell diagram looks like. We've now measured the distances to millions of stars, and hence we've got the luminosity of millions of stars. And we know the colors of those stars. So the Hertzsprung-Russell diagram is no longer a cartoon, it's actual data. Every dot there is an actual star whose color and luminosity has been measured. And there are so many of them in the main sequence that the dots are simply too close together, so we've then just colored them as to how many dots there would be in that particular pixel of the Hertzsprung-Russell diagram. So this isn't a guess of what we think the stellar evolution of the population ought to look like. This is an actual population of the Milky Way. So now we can start to say, well, we think we understood stellar evolution because we think this is how main sequence stars change into red giants, and that's how red giants change into white dwarfs. now we actually know the population of the galaxy, or at least this half of the galaxy. And so we can actually test our ideas of stellar evolution. Along the way, there were a few surprises. Gaia actually found a few sun-like stars, stars very similar to our own, but orbiting with a neutron star. Now, neutron stars are the result of supernova. How can you have a supernova and a sun-like star is left behind next door to it? But apparently there's a few of them. There's something like 20 that it's found, where it looked at these stars, they're sun-like stars, they're moving through space, and they are moving in circles because of parallax, but once you've taken account of all of that, they are still orbiting around something we can't see. That something we can't see is not massive enough to be a black hole, but it's totally non-luminous, and the only thing we can think of that's massive enough and non-luminous, or at least low luminosity, is a neutron star. So it appears to be lots of sun-like stars are orbiting neutron stars. And the question is, does that change the way we think about supernova? Because it is possible to survive a supernova, apparently. More work needs to be done there. We've also determined, by looking at where the stars are in the Milky Way, we've determined that the Milky Way disk is warped. There's a representative cartoon, if you like, of what it might look like if we were able to step outside the Milky Way and look back at it. It's still two fried eggs back to back, but now it's two fried eggs that look a little bit warped. We know from other galaxies, like this one, that that happens. It's a little difficult to see, perhaps, but if you look at the dust lane in this galaxy is ever so slightly S-shaped. It is slightly warped. So we have seen other galaxies that appear to be warped, and it now looks like the Milky Way is warped. We believe that the warping of a spiral galaxy is the result of gravitational interactions with other galaxies. We've seen it in other cases. It's no surprise in that sense that the Milky Way is warped, but instead of assuming it might be, we now know it is. If you look at individual stars and map them out, remember we're looking at stars as a function of time over a period of 10 years, so we know how stars are moving in the Milky Way. Here the sky is unwrapped and some of the stars are shown as small streaks. From that, we can get an indication of how the stars are moving. Some of the stars are moving exactly like you would expect them to. They are going around the Milky Way in the plane of the spiral arms of the Milky Way, and they appear to be moving in a speed that's consistent with orbiting the way the sun does. We take a couple of 100 million years to go around the center of the Milky Way. But there are some stars amongst the billion that they've seen, some stars don't appear to be orbiting the way you would expect. Some are going backwards. Some are going over the top in polar orbits. Some have got extremely elliptical orbits that appear to be hurtling in towards the center of the galaxy and then presumably will come out again. So it's not simply a question that every star is doing a nice sedate circle, much as you would expect if you had a multi-lane motorway and all were going at the relevant speeds. So how can you account for the fact that some stars are going backwards and some stars are in really weird orbits? Well, you come to the conclusion that the Milky Way has interacted and merged with other galaxies in the past. Again, that shouldn't be a surprise because we see collisions of galaxies when we look out there. We see galactic mergers, we see galactic interactions, we see tugs of war, we see mergers in process or the results of mergers in the past. So it's no surprise that we now have evidence that our own Milky Way is the result of galaxy mergers. But instead of an assumption, we now have the evidence. So that is only a sort of schematic family tree. That doesn't necessarily represent exactly what happened in terms of previous mergers. But we can pin down with some precision what has happened in the past. Here's a timescale from the Big Bang on the left to the present day on the right, either in time since the Big Bang or on the bottom scale, time before present, with 0 on the right and Big Bang on the left. We know there have been a number of encounters with a number of galaxies. I'm not going to go through all of the details. Some of them have got wonderful names, like we have encountered the Kraken before, and we have encountered Enceladus. Enceladus and Sagittarius, etc. And you can see we don't know exactly the timings, but to within 1 billion years or so, we can say that we did have an encounter with this galaxy between 1 and 2 billion years after the Big Bang. And we did have an encounter with Enceladus. How do we know? By working backwards from, this is the way the stars are moving. The only way we can understand the stars moving in this way is if a galaxy hit us from this direction and caused a lot of stars to go in weird orbits. We can also start to pin down the history of not necessarily individual stars, but certainly star clusters. We now know, for instance, that some of the globular clusters in the Milky Way are not ours. We robbed them of other galaxies. It is thought that quite a few globular clusters from the Enceladus galaxy were effectively stolen from Enceladus. Enceladus merged with the Milky Way, and those globular clusters became ours because we were bigger than it was. And there have been other encounters where we've stolen stars and stolen globular clusters. One of the more interesting ones is the one on the right there, the Sagittarius dwarf galaxy. You can see that it goes to the right and it doesn't have an end cap because that particular encounter is still happening. This is what we think has been happening with the Sagittarius dwarf galaxy. I'll just call it Sagittarius from now on. We think that Sagittarius dwarf galaxy interacted with the Milky Way about 6 billion years ago and produced a whole load of new star formation in the Milky Way. That Sagittarius galaxy got stretched out into a star stream, but it came back again and hit us a second time 2 billion years ago. And that star stream continued and encountered the Milky Way again with a glancing blow about 1 billion years ago. You can see tidal effects of two galaxies getting too close to each other tends to drag out a galaxy into either, you call them tidal tails, or you might call them star streams. And that is a star stream that now exists because we have had multiple encounters with Sagittarius. One of the most interesting is the one I first noted there. The first encounter with Sagittarius was about 6 billion years ago. Whenever you have two galaxies that encounter each other, we've seen this with other galaxy collisions. Whenever you have two galaxies that encounter each other, you tend to get a riot of new star formation because one perturbs the other. The hydrogen clouds in one get perturbed and start to collapse and produce new stars. So there was a new set of star formation about 5 to 6 billion years ago because of Sagittarius. That is when our sun was born. So perhaps our sun was born because the Sagittarius dwarf galaxy clipped the Milky Way and is sort of still doing so, but it has produced new star formation rates. And the timing is right. We can't prove that the sun was born because of Sagittarius, but the timing is about right. We know there was a peak in the birth rate, as it were, and that's when our sun was born. So maybe we owe our existence to the Sagittarius dwarf galaxy. When we look at other galaxies, we see these star streams. Sometimes they're quite faint. If I take that image and invert it and bump the contrast up, you can see those star streams. So that galaxy definitely had an interaction with other galaxies, and it left this breadcrumb trail of stars behind it, much like the ones we see for Sagittarius. M63, it looks a bit like a galaxy completely on its own, completely isolated. We do the same thing, invert it and bump the contrast up. Actually, there's tidal tails and star streams all over the place. M63 definitely had interactions in its past. And again, this one is perhaps, you can sort of see a fuzzy glow around it. Again, we invert and bump the contrast up. It is quite obvious. It's not necessarily loops, but there are quite definitely star streams indicating that this galaxy has had interactions in the past. And the more galaxies we look at, the more often we see these signs of interactions. Cannibalism of galaxies, galaxy mergers, galaxy collisions is not something that's odd. It is an intrinsic part of galaxy evolution. It is how galaxies change. It is how galaxies grow. The Milky Way is the size it is, 100,000 light years in diameter, because we've eaten other galaxies that were smaller in the past, and we have grown accordingly. Not only can we look at what the stars are doing and say the only way we can explain this star orbit is to say we've encountered these things in the past, we can also do a certain amount of what's happening in the future. Because again, we can look at stellar parallax. It's pretty amazing, but not only can we get stellar parallax for stars in the Milky Way, which is amazing enough in itself with a resolution of 10 micro-arc seconds, but actually we can even see parallax for stars in other galaxies. So we know that there are going to be changes. The Sagittarius dwarf galaxy will continue to hit us every once in a while, but there are two mergers that are going to happen in the future, approximately 2 to 3 or 4 to 5 billion years into the future. The first one is the LMC, the Large Magellanic Cloud. It is possible to measure parallax in the Large Magellanic Cloud, despite the fact that it's 170,000 light years away. What is even more incredible is they are just about at the point of being able to measure parallax in the Andromeda galaxy. 2.5 million light years away, and we're trying to measure the change in angle because the Earth is going around the sun. Nearly a few million miles compared to millions of light years. The angles are absolutely tiny, but it's hoped that when we get the full 10-year data release, we hope to be able to measure the parallax of stars in the Andromeda galaxy accurately enough to tell what those stars are doing. Are we going to have a head-on collision with Andromeda? Is it going to be a glancing blow? We know it's coming towards us. We're not quite sure what that interaction is going to be, but we know it's going to happen in a few billion years. So let me wrap up because I've already taken my time. Gaia took data until early last year, January 2025, and it was finally retired in March of 2025. It was put into a retirement orbit, which sounds very graceful, doesn't it? Sounds so much better than a graveyard orbit. With L2, just like the James Webb, you can't let these things go beyond L2. When a satellite comes to, or a spacecraft comes to the end of its life, they push it beyond L2, and that's it. It will never orbit L2 again. Once you've pushed it beyond L2, it will simply continue to go around the sun. It's no longer at the Lagrange point. It will no longer stay put. It will then orbit the sun. It might come back again eventually because it's orbiting the sun with a particular period. But basically, once you pushed it away from L2, it's effectively dead. As it drifted away from L2, some astrophotographers actually caught it. That S in the middle there is Gaia moving away from L2. Perhaps it'll be back in 14, 15 years, and it might be another photographic object, perhaps, when it comes back closer to Earth. Just before they shut it down completely, they asked it for one final data dump, and it gave this little message. And notice the color coding. It basically said goodbye, and then it was shut off completely. Is there going to be a Gaia 2? Probably not. But in a very short length of time, we're going to have the Nancy Grace Roman go up. They've brought the launch forward. Originally, they said it would launch in 2027. NASA have now said the Nancy Grace Roman Space Telescope would launch in 2026. It's ahead of schedule. I think they want to get it up there before a certain president cancels it. I think that's the idea. Nancy Grace Roman is not Gaia 2. It will be able to measure the positions of stars. Because it's an infrared telescope, it will be able to look at very dense, dusty regions like the center of the galaxy, and it will be able to measure the positions of stars relatively accurately. It's got a huge chip. This is the actual relative size of the chip compared to the Hubble Space Telescope chip. You know the resolution of the pillars of creation that Hubble obtained various times during its life. There's the Nancy Grace Roman chip to scale, and it is the same resolution. So you can imagine the wonderful resolution we were getting from Hubble. Imagine something 100 times bigger, but with the same detail. So the Nancy Grace Roman is going to be able to cover huge chunks of sky. It's working in the infrared, so it will be able to look into the center of the galaxy and hopefully get parallax of some stars in there. And it might be able to do a better job than Gaia under certain circumstances, but that's not its main aim in life. Gaia has produced an awful lot of data. Data release 4 is estimated to be approximately 500 terabytes of data. Positions, brightnesses, colors, spectra, etc. And somebody's got to sit down and look at that data. So yes, an awful lot of people are going to be trawling through that data. I'm sure they're going to use AI tools to help them trawl through that data to try and make sense of it, some of which we've already been doing, and we've been using that to get information about the Milky Way, about the dynamics of how stars are moving, which helps us understand the Milky Way evolution. It helps us understand what has happened in the past. What galaxies have we interacted with? Why are these stars doing that? Why have we got these globular clusters? So Milky Way dynamics and evolution will continue to develop because we'll have more and more data with data release 4 and data release 5. Remember that it's not all about the Milky Way, because in some cases, simply knowing the distance to stars means that with their brightness, we've got their luminosity. So with their luminosity and their color, we've got essentially all we need to know about the star's mass and age, and to some extent, chemical composition as well, especially if we've got the spectra. And therefore, we can test all of our ideas about stellar evolution because we now have billions of stars catalogued and hundreds of millions of spectra on file, as well as billions of colors and brightnesses and distances. Along the way, we've also picked up some information about neutron stars. Gaia also found a black hole that we didn't know existed. And we've got information about the solar system. And it's also by accident picked up a few exoplanets. Because it's measuring the stars with such precision, it's actually picked up that some stars are wobbling because of planets going around them. Data release 5, which should be coming along in a few years' time, containing all 10 years of Gaia data, might give us the precision whereby we can look at many billions of stars with sufficient precision to get really subtle changes to positions of those stars. Maybe we'll get a handle with enough data on the nature of dark matter and dark energy if we've got the precision and if we've got the numbers of stars. So hopefully data release 5 will allow us to get more and more about dark matter and dark energy. Gaia has often been described by two words: obscurity and ubiquity. Obscurity because it's nowhere near as famous as its cousins, the Hubble Space Telescope and the James Webb Space Telescope. But ubiquity because Gaia data is everywhere. Gaia data is being used by every ground-based telescope. Gaia data is being used by every space telescope. Gaia data will be used by every astrophysics research project for the next 10, 20, 30 years. Gaia data is Gaia's legacy. Thank you very much.